Hello, welcome to my channel. Here we are discussing questions from the topic electricity for Edexcel AS level physics examination, that too from the past 4 to 5 years of Edexcel board examination question paper. Before we start, please like and share my videos and also subscribe to my channel so that you can get notification about my new videos. In fact, these videos are good for other exam boards also, since almost all exam boards include questions from electricity. This is the first video of the series, and the link to the second video of the series will be given in the description box soon. And I shall show you how to answer these questions. So let's start with question number 1. A student carried out an experiment to determine the resistivity of a metal in the form of a wire. She made the following measurements. She made the measurement for the length, resistance, diameter, etc. And also there is a table provided for different metals, its corresponding resistivity. Now the question is, determine which is this metal used here. Determine the metal of the wire used for this experiment. So we have to calculate the resistivity of the material or resistivity of the metal, and from that we can decide it. Let us have a close look on the informations given. The length of the wire, it is given. It's given as 0.2 meter. Then the resistance of the wire, it is given as 50 milliohms, and we have to convert this 50 milliohms to ohms. So milli means dividing by 1000, which is same as dividing it by 10 to the power of 3, or this will give the same effect of multiplying with the minus 3. So here afterwards, better you follow the prefixes. Whenever you see the prefix small m, milli, you can multiply with the 10 to the power of negative 3. Then what about the next information given? This is the diameter given here. Diameter is 0.36 millimeter. So we have seen in the previous case that whenever the prefix milli comes, you can multiply the term with the minus 3. So it is 0.36 times, to change milli, multiplying with the minus 3, this much meters. We know the equation for resistance, or we know the relation connecting resistance and resistivity. The relation is R equals rho L over A, the area of cross section. So here it is only the diameter is given. Of course, we need the radius from this, which is half of this number over 2. So the radius is 0.18 times 10 to the power of negative 3 meters. This is the radius. Now, usually the wires are cylindrical in shape. Cylindrical, so for the cross-sectional area, cylinder. So cylinder. So its cross-sectional area is like a circle. So we need the area of the circle. Area of the circle is pi r square. So in our equation, we will substitute the value. So let us start from the main relation, and we have to calculate the value of rho. So keeping rho as the subject, we can rewrite the equation of the form R A times L. Then let us start substituting the numbers. The resistance of the wire, we changed into ohms. So let us substitute the number. The resistance is 50 times 10 to the power of negative 3, and the area pi r square, it is pi times the radius 0.18 times 10 to the power of negative 3 pi r square. So the whole square, the whole thing divided by the length. Length is 0.20. Please make use of your calculator for calculating the answer. On calculation, it is giving you an answer of it is 2.5 times 10 to the power of negative 8. The unit for resistivity is ohm meter. So this is the answer we are getting. The resistivity of the wire calculated using the information, it is 2.5 10 to the power of negative 8. But the question is, which is this metal? So let us compare this number with the numbers given. Of course, the nearest value is the first one, 2.7 10 to the power of negative 8. Therefore, the metal used is aluminium. So this is the information, the metal used. Metal used is aluminium. Now let us move on to the next part of the question. State what is meant by drift velocity. So drift velocity is, it is the average or mean velocity of the electrons flowing through the wire. So let us put it as an answer. It is the average or the mean velocity. Electrons flowing through the wire. Now let's move on to the next part of the question. A copper wire has a cross-sectional area. So whatever it is given, let us symbolize it. It is cross-sectional area A and carries a current. So it carries a current here. You have to calculate the drift velocity and N is also provided. The question says that, the first part of the question, it says that use the equation I equals NQVA. So this is the equation we have to use to calculate the drift velocity. So starting with the relation I equals the current flowing, it is the product of number density. N is called the number density. The electron density times charge of the electron times the drift velocity times area. And here we want to calculate what is V. So keeping V as the subject, it is I over N Q E A. All the values are provided here. The current is, it's given in amperes, 1.31 over the number density is 8.49 times 10 to the power of 28, but it's a long big number. Q. Now the charge of the electron, this is negative 1.6 times 10 to the power of minus 19 coulombs. So this is what we are going to use as the charge. So let us write the value of Q here. It is negative 1.6 times 10 to the power of negative 19 times. Now the last one is the area. Area is also provided here, which is 2.64 times 10 to the power of negative 7. All numbers are given here. Area 2.64 times 10 to the power of negative 7 meter square. Current I is given, N is given, all these numbers are given. So please make use of your calculator to find the final answer. You are getting an answer of negative 3.65 times 10 to the power of negative 4. It is the speed, so it is meter per second. This is the drift speed. Now let's see the next question. Resistors are included in circuits that are used as potential dividers. Potential divider. derive an equation for the combined resistance RT of two resistors R1 and R2 in series. See, in potential divider, we are connecting resistors in series. So if we want to divide this power source given, we are connecting resistors in series across the power source. So let's see that type of a potential divider circuit here. So imagine we have a battery source. We are connecting two resistors R1 and R2. So it is a potential divider arrangement. Let's call it as first resistor R1 and second resistor R2. Now, since it is a series arrangement, series connection, we know that. Let us say this is the voltage of the first one and this is the voltage of the second one. Second resistor. Voltage drop across the first resistor and the second resistor. And again, since it is a series connection, we know that the total voltage applied, let us call it as the total supply voltage. This total supply voltage or the battery voltage is distributed among these two resistors R1 and R2. That means the total voltage is the sum of V1 and V2. The total voltage is distributed, shared by these two resistors according to their need, according to the resistance value. So V is V1 plus V2. Now let's write, now imagine there is a current of I flowing through starting from the voltage source, starting from the battery. And we know that since it is a series connection, the same current I is flowing through both resistors. So we can write how much is V1. According to Ohm's law, voltage is the product of current and the resistance. So V1, the corresponding resistance is R1 plus for V2, the same current and the corresponding resistance is R2. Now let us take I as a common factor. So we can write R1 plus R2. Now at the same time, let's write how much is this V. This V is the current times the total resistance. Because this is a total. V is like the total voltage supplied to the circuit. So total voltage is current times the total resistance. Total resistance means this is the total resistance. Okay, resistance combined value of V1, R1 and R2. So V is the total resistance multiplied by current. Now here from left and right we can cancel this I. Therefore, the rest of the equation is appearing as RT is the sum of R1 and R2. So this is the equation for the total resistance. So from here I'm coming here. So RT equals R1 plus R2. This is the equation for RT, the total resistance for the two resistors when they are connected in series. Connected in series, the value for RT, it is R1 plus R2. Now let's move on to the next part of the question. The diagram shows a circuit that includes a resistor combination. The battery has a negligible internal resistance. So we are not considering the internal resistance. So R is equal to 0. Now the question is, the ammeter displays a current of 0.5 ampere. So let's write here the circuit current. Ammeter displays a current, the circuit current 0.50 amperes. This is the current, circuit current. Calculate the resistance value R. Now here you can see a loop of resistors. This loop. It's a loop of resistors connected. It's a combination, series parallel combination. 6 ohm connected in series with a combination of R and two fixed resistors connected in parallel. So the total resistance will be 6 plus the resistance of this part. Okay, so before that Let us see how much is the total resistance that can be. For the circuit, how much can be the total resistance? We know the total voltage applied and we know the circuit current. Therefore, we can calculate the total resistance. So let us calculate the total resistance. R total, that is for this dotted box, the total resistance. R total is the total battery voltage, V battery, V power supply over the circuit current, which is 7 over 0.5. This will be giving a value of 14 ohms. So total resistance is 14 ohms. But our question is, what is the value of R? This is what we have to calculate now. In this loop, one of the resistor R is unknown. That value we have to calculate. But so this total resistance, it is RT. Now, let us concentrate on that loop. So total resistance RT, it is a sum of 6 plus, that is the first resistor, this one, 6 plus. It's a parallel combination of R parallel, then it is a series combination of 8 and 16. This is the total resistance. Now let's see how much it is. It is 6 plus, and of course on the left side, instead of total resistance, we can substitute it as 14. Now it is R parallel, 8 plus 16, it is 24. Okay, R parallel 24. So 14 minus 6 equals R parallel 24. That means 8 equals R parallel 24. Now, let us find out the resistance R parallel 24. What is the combined resistance? See, you have studied, so now these two are connected parallel. So you have studied that the combined resistance of two components, two resistors connected parallel, it is the sum of the reciprocals of the individual resistors. This is what we have studied. Total resistance for a parallel combination, it is the sum of the reciprocals. And I can give you an easy way to calculate when two resistors are connected. When two resistors, so this is a method exclusively for two resistors connected in series, in parallel, I mean, two resistors in parallel. When two resistors are connected in parallel, directly we can calculate the R total by dividing the product of the two resistors with the sum. This way we can directly calculate. Please remember, this is exclusively for two resistors connected in parallel. R total is R1, R2, the product over sum. Okay, so in this case, now I want to use this method here. So here I can write 8 equals, the resistors are R and 24. So the numerator is the product. So it is 24R over the sum is R plus 24. Now, just by the method of algebraic calculation, you can, so now let us take R plus 24, 24R equals 8 times R plus 24. 24R is 8R plus 192. Then I'm transposing 8R to the left side. 24R minus this one, I'm transposing this to the left side. 24R minus 8R, which is 192, or 16R is 192. Therefore, R is 192 over 16. On calculation, you will get an answer of 12 ohms. So this is the answer for the value of R. Okay, so we have the total resistance for the loop, which is 6 plus the parallel combination. Then R total we already calculated, so we can equate with that R total, and we are using this simple way of calculating the total resistance for two resistors, and when we are substituting all these numbers, finally we are getting an answer of 12 ohms. Let's see the next part of the question. The circuit shown below includes a light independent resistor LDR. The battery has no internal resistance. In normal day, this particular type of LDR has a resistance of 670 ohms. Calculate the power dissipated in the fixed resistor in normal daylight. Resistance of the fixed resistor is 8 kilo ohms. So it says that this is our LDR, and resistance of the LDR on normal daylight, this is R of LDR. R of LDR is 670 ohms. Then the fixed resistor R value, R equals, this is kilo ohms. Kilo means multiplying with 1000 or 10 to the power of 3, which is 8000 ohms. So I'm writing it here. This value is 8000 ohms. So we know the value of both the resistors. Now the question is, calculate the power dissipated in the fixed resistor. So this power, how much is the power dissipation, PR? How much is the power dissipated by the fixed resistor R? And we have studied the equations for power. Power is the product of voltage and current. Then when you are substituting an equation for voltage, as like voltage is I times R. So this is for voltage times. So this voltage I substituted it as IR times I. So I'm getting an equation. It is I square R, an equation for power. Similarly, if you substitute for I, there is one more equation for power, which is V square over R. So these are the three equations we are using to calculate power, and especially power dissipations we are calculating with the equations I square R or V square over R. Now here they are asking you what is the power dissipated across R. So power dissipated. Power dissipated in R. So let us use the second equation I square R. But we don't know how much is the current I. We will find out that also. So it is I square R. This is the equation I'm going to use. But for that, let us calculate how much is the circuit current. We know how much is the circuit voltage, total voltage applied we know, and also we know what is the total resistance, R total, which is the sum of these two. So let us do that part first. R total is 8000 plus 670, which is 8607 ohms, and therefore current I equals 12 over 8670. This will give a current of 1.38 times 10 to the power of negative 3, 10 to the power of negative 3 amps. This is the current. So let's use this current we are using here. So power by resistor R. So power of resistor R, it is I is 1.38 times 10 to the power of negative 3 the whole square times resistance is 8000. On calculation, it's giving an answer of 0.015 watts. Okay. Now, the same question, if you want, you can do with the third equation also. So P, of resistor R equals V square over R. I can use this also, but here you have to calculate what is the voltage of R. Voltage of R is I times R, which is 1.38 times 10 to the power of negative 3 times 8,000. This is on calculation 11.07. 11.07 is the voltage across R. Now this voltage across R, I can use it here. Okay, here I can use that voltage, which is 11.07 the whole square over resistance 8,000. On calculation, you will get the same answer, 0.15 watts. So I'm just showing you, you can use the equation power dissipation as I square times R, or it is V square over R. Both the way you get the same answer. Now let's move on to the next part of the question. As the light intensity incident upon LDR decreases, the power dissipated in the fixed resistor decreases. Explain why the power in the fixed resistor decreases. They are telling power of the fixed resistor, it is decreasing. Power of the fixed resistor decreases when the light intensity of LDR increases. Okay, what is the reason? But you have to include reference to the electrons in the LDR. You know, LDR, it is a light dependent resistor. So let's start with as light intensity decreases, as light intensity so let us write L. Light decreases. Light decreases means, so what's happening? You have to mention about the electrons. So when the light decreases, the number of free electrons or conduction electrons decreases. So light is, it's a form of energy you are supplying. Okay, light means light energy. So light energy, the energy supplied decreases. So when the energy supply decreases, the number of free electrons or conduction electrons available is also decreasing. And in metals or semiconductor materials, when the energy supply decreases, the electrons emitted by thermionic emission decreases. So that idea I'm going to write it here. When light decreases, the light energy supplied decreases. I'm using the symbol decrease, but make sure exam you are writing the full words. So light energy supplied decreases. So the electrons, the number of free electrons or conduction electrons decreases. So the number of free electrons, or we can say the conduction electrons available decreases. This is by thermionic emission. No, not thermionic emission. This is by the emission with the light energy. Sorry, this is by emission by light energy. That number of electrons emitted with the help of light energy decreases. Number of electrons that become free by absorbing light energy decreases, because energy decreases, so number of electrons releasing or number of electrons become free electrons decreases. Therefore, as a number of free electrons decreases, we can say that the current or we can say the resistance, number of electrons decreases means the resistance of LDR increases, or I can say the current of LDR decreases. As the number of free electrons decreases, the current of the LDR is decreasing. Current of the LDR or current in the circuit, because the LDR is connected to the circuit in series. So current of the circuit decreases. So current of the circuit decreases means the voltage drop across the resistor decreases. This is by Ohm's law. Ohm's law, and R is fixed. Since R is fixed, when current decreases, the drop across the voltage decreases. Therefore, we can say that, or from here we can say that the power dropped or power dissipated by the resistor decreases by the relation power equals V square over R. Because the question demands explain the power dissipated across the resistor decreases, your answer should include reference to the electrons in the LDR. So light intensity decreases means light energy supply decreases, so number of electrons, free electrons available decreases. That means the resistance is increasing, or number of free electrons decreases means it is this one. From here we can say the current is decreasing or resistance is increasing. So the voltage drop across the resistor decreases and the power decreases. Now the next question is about a potato cell. The student is doing an experiment using potato as the source, potato cell. Complete the diagram below to show the circuit that could be used in order to determine the EMF and the resistance R. This is just a circuit diagram they are asking. And we know that to calculate E and R, we need how much is the current flowing through the circuit, what is the voltage, all these things we have to know. So for that, definitely we need an ammeter, and also we need a voltmeter. Okay, so let us try the circuit. So we need an ammeter, and we need a variable resistor to vary the voltages, to vary the load. So this variable resistor is representing the load. Then if you want, you can use a cell, or there is the key also, switch also you can use. So an ammeter. Now where will we connect the voltmeter? It's of course it's not across the resistor here. You have to connect the voltmeter across the cell, potato cell. Here we are connecting the voltmeter. Now the voltage, whatever we are getting when a current is taken from, so this shows that there is a current flowing. The voltage across the cell when a current is flowing or taken from the cell, we call it as a terminal PD. So now the voltmeter is giving you the terminal PD. So to know the terminal PD, you connect the voltmeter across the cell. So an ammeter, voltmeter, a variable resistor. Now the next part of the question is, the student from his experiment, he plotted a graph and voltage along y-axis and current along x-axis. Use the graph to determine the values of E and R, EMF and R. It's a 4-mark question. So you have studied the graph relating the terminal PD, that is the voltage and the current along x-axis and terminal PD along the y-axis. The graph is having a negative gradient. It's a line sloped down, negative with a negative gradient. And You studied that graphically. If you are extending this graph, wherever you get the y-intercept, this y-intercept, this is the EMF. And the gradient, this gradient, this is negative R, internal resistance. This is the method. So let's make use of the same method here. So first part, you have to draw a line of best fit. But when you draw the line of best fit, okay, I drew a line of best fit. Use your ruler to draw the line. And let me join this one, that line, to the y-axis, and I'm getting the y-intercept as almost 0.29 volt. So this is my EMF value. So let's write it here. Find the value of EMF. So I'm writing the beginning itself, I'm writing EMF E, it is the y-intercept. Y-intercept of the graph or the line. And we are getting it as 0.29 volt. This is the EMF value we are getting. Please look it again. My line of best fit is not looking very neat, but draw it neatly with your okay, and extend it backward to get the y-intercept. I've done it here. Extend it backward to get the y-intercept, and the value is 0.29 volt, because each small square is after 0.25, 0.26, 27, 28, 29. So 0.29. Then the gradient is negative internal resistance. So let us find out the gradient. For that, let us take any two values from the graph. So let me take a point here. What are the values of x and y coordinates for the points? 4, 5, and the current value, is it 1? Um, no, this is coming like a point, this point I'm taking. Okay, I'm taking this point, and I am taking this point. These are the 2 points I'm going to take. So let me draw the triangle. You can draw the triangle, or okay, from here I'm drawing the triangle. Let me write the x and y coordinates. For this one, 0.44, 0.44. Please don't forget to take this milliamps. So it is 10 to the power of negative 3. This is the x coordinate. And the y coordinate is 0.9. 0.09. So this is the x and y coordinates. Similarly, for this, the x coordinate is maybe 0.06. That means this point, this point, this point, and this point. And the y coordinate for this number is 0.26. Oh, don't forget into the power of negative 3 times 0.26. That means this is the point, and this is the point. 9, 9. These are the 2 points. Okay, so you can If you want, you can show that as a triangle. This is the triangle. Now from here, the gradient equals negative r. So let us calculate the gradient. Equals delta y by delta x. That is the difference in the y components, it is 0.09 minus what is the y component, 0.26. It is 0.26 over, then the x coordinates are 0.44 minus what is the current value here, 0.46. It's not 46, 0. Not 46, 0.06. 0.06 times 10 to the power of negative 3. This is on calculation. It is giving a value around 405. Approximately, it is giving a value of 405 ohms. But the gradient is negative R. The gradient is negative. So this is the number it is giving. I'm not writing it here, 405. But we know that the gradient is negative of r, and also there is a minus sign here because there is a minus sign, minus 4.5. The gradient is negative of r, therefore r is negative of negative 4.5, which is positive 405 ohms. This is the resistance we are getting. Now let us move on to the next part of the question. It's separate experiment. Two resistors are connected with the internal resistance R. We are not ignoring the internal resistance here. Resistors are connected in series. Then they are connected in parallel. But the question asked is, in which of the cases the terminal PD is greater? Which case the terminal PD is greater? This is the question asked. So there is a series connection and there is a parallel connection. Okay. Since it is like a comparison, I'm also doing that way. This is for diagram A and this is for diagram B. Now here the two resistors are connected in series. Therefore, the total resistance will come as R plus R, which is 2R. But here the resistors are connected parallel. I hope you remember the method I gave you in the previous question. When two resistors are connected parallel, the total resistance we can calculate by their sum over, the difference over the sum. So here R square over 2R, when you are cancelling 1R, you are getting the total resistance as R by 2. So here the total resistance is coming as just R by 2. So I'm writing it here. R total will come as R by 2. Half of each resistor. Now, let us see what is the current flowing. Okay. So we have written already that we have calculated already the total resistance. R total, it is 2R. And here R total is equal to R over 2, R by 2. Therefore, what is the current? Current is whatever is the battery voltage over 2R. But in this case, the current will be V over R by 2, which will give an answer of 2 V over R. Sorry, 2 V over R. See, this is half of V over R, and here it is giving a value 2 times V over R. This is the current. So when you are comparing the current, it's very obvious that the current in circuit B is higher, 2 times V over R. Here it is half times V over R. So circuit current is more in B. So I'm writing this part first. More current flows, more current flows. Here we are not ignoring the internal resistance. So the terminal PD is given by the equation E minus I times R. Okay. So more current is flowing means more lost volt. Therefore, the terminal PD decreases. So I'm writing that also here. I'm writing it here. More I makes more a lost volt. Lost volt means I times R. So V decreases. Whereas what is happening in the circuit, I'm just going to call it as V in the second circuit, VB. What is happening in the circuit? Here compared to B, less current, half of V by R only flowing. So here less current flows. Less current flows means the terminal PD is E minus IR. So from here less I makes lost volt lesser. Lost volt less. So what is happening to the terminal PD? VA increases. So our final conclusion is terminal PD in circuit B, circuit A is greater than terminal PD in circuit or diagram B. So we calculated the total resistance, then we calculated the total current, and we did a comparison like the current, in which case more current is flowing. The current comparison we are doing here. So we found that less current is flowing through diagram A. That means less lost volt. Lost volt means this part, IR. IR is the lost volt. Less I makes lost volt less lost volt. More I makes more lost volt. Therefore, terminal PD increases in circuit A. So PD in A is more than the terminal PD in figure B. Let's move on to the next question. Explain how the circuit should set up to keep the. So what is this question? Look at the circuit. There is a battery, then there is a fixed resistor R, and there is a thermistor. Okay, R of the thermistor, resistance of the thermistor. So this is a potential divider arrangement across this battery. As the temperature changes, the potential difference across X, Y and V Z changes. So as temperature changes, the voltage potential difference, this is Vx. So this is voltage Yz, and this is the voltage Xy. Voltage across points X and Y means voltage XY I represented that way. So now the question is, Such a circuit can be used to operate an air conditioning unit in a hot classroom in order to keep the classroom cool. The air conditioning unit starts operating when the PD in the secondary circuit exceeds a certain value. PD in the secondary circuit. So the secondary circuit is this air conditioning unit. So air conditioning unit is the secondary circuit. Okay. Another circuit other than this what is shown here, that is the AC unit. Now the question is how they or where you should connect. Your answer should include details of how a negative temperature coefficient thermistor works in terms of the particles. Explain how the circuit should be set up to keep the classroom cool. How means where you have to connect it. You have to connect it across, whether you have to connect it across resistor R or connect it across the thermistor. This is the question they are asking. But when you are writing the answer, you should include about the negative temperature coefficient in terms of the particles. Okay. So thermistor, we know that it is a temperature dependent component. The resistance of its thermistor depends on the temperature. So here what's happening is as the temperature of the temperature given to the thermistor increases, what's happening then the number of conduction electrons also increases. So temperature is supplying temperature means heat means supplying energy. So when we are giving energy in the form of temperature, heat energy, more electrons become free by thermionic emission. They absorb heat and from heat energy, they absorb energy and more electrons become free as free electrons. So this process we call it as a thermionic emission. So as more electrons become free, we can say the current increases. More electrons are available for conduction. So the current in the circuit or current in the thermistor increases, or in another way we say the resistance of the thermistor decreases. So let us write that part first and then we will come to the second part of the question. Second part is where to connect. Where to connect the secondary unit. This is the second part of the question. So let me write the first part of the question. It is like as the temperature increases, what is happening? The number of free electrons, the number of free electrons also increases. Actually, this is because heat energy, when we are supplying heat energy, it is thermionic emission. This is by thermionic emission. When we are supplying energy, the material absorbs energy and more electrons become free. Okay, the number of free electrons also increases. Then when more electrons are flowing means more current is passing through the LDR. When more electrons flowing means or more electrons passing means the resistance of the LDR decreases or the current through the LDR increases. This is what is happening. So when more energy is supplied in the form of heat by thermionic emission, more number of electrons become free. When more electrons are flowing, current of LDR increases or resistance of LDR decreases. So that is what we say that. So the resistance of the LDR is inversely proportional to the temperature. So when you are increasing the temperature, the resistance is decreasing. Okay, so there is a negative relation or inverse relation between LDR and the temperature. So we say that LDR is having negative temperature coefficient. That is, LDR is having negative temperature coefficient of resistance. So it is having a negative indirect proportion or negative temperature coefficient. So we have answered the first part because it says that your question, your answer should include the negative temperature coefficient of thermistor in terms of particles. Particles means electrons. Now we are going to answer the other part, how the circuit should set up. So here we reached till the point the current. So now I'm continuing as current of LDR increases. What is I'm sorry, yeah, current of LDR, current passing through the circuit or current of LDR increases. The voltage drop across LDR is also, the resistance is decreasing, the current flow increases. So as the now we can write it in terms of the resistance. So we have seen that as resistance of LDR decreases, the drop across LDR decreases. The voltage drop across LDR decreases. That is, voltage YZ decreases. So the voltage of the fixed resistor increases. It has to increase to keep battery voltage fixed or same, to keep the battery voltage same. So as the resistance of LDR decreases, the drop across LDR decreases. This drop is decreasing according to Ohm's law. Ohm's law. V is equal to I times R. When R decreases, the LDR voltage is decreasing. Therefore, the voltage of the voltage drop across the fixed resistor is increasing. So this means this VR means that is VXY. XY increases. So VXY is being controlled by the thermistor. Because this is the case when the temperature is increasing. Similarly, if the temperature decreases, Vxy decreases. Voltage across the thermistor increases and voltage across Xy is decreasing. So both the ways it is controlled by the thermistor. So the secondary circuit should be connected across XY. That is the secondary circuit connected across the fixed resistor R, or we say connected across XY. XY, that is across fixed resistor, that is across R. This is the place to connect the secondary unit. So we included the answer. We included the negative temperature coefficient. So as the LDR resistance decreases, the voltage of the LDR decreases by Ohm's law. Therefore, the resistance across the fixed resistor has to increase to keep the battery voltage same, or Vxy is being controlled by the thermistor. So we have to connect the secondary unit across that Vxy. Now the question is, next part is, calculate the change in resistance of the LDR when the light is shown on it. So there again, there is an LDR is used here, not thermistor, LDR. Fixed resistance has a value of 1.2 kilo ohms. So the value, it is 1.2. So it is 1.2 times 1000. So it is 120. So R is 120 ohms. Not 120. It is 1200. Sorry, 1200 ohms. 1.2 kilo ohms or 1200 ohms. Then an EMF of 12 volt. So here EMF is 12 volt and a negligible internal resistance. Initially, the circuit is in darkened room and the voltage displayed is 4.71. Then when it is kept in a lighted room, it is 2.61. Calculate the change in resistance of the LDR. Calculate the change in resistance of the LDR. So, two cases are given here. One is it is connected in the darkened room and the other one it is connected in the lighted room. So let us see here also. Let us see first one in the darkened room. Darkened room. This is the lighted room. Okay. So we have seen here in the darkened room, fixed resistor has a resistance of R is 1200 ohms. Here also R is 1200 ohms. It is not changing. The EMF for the voltage is 12 volt. EMF is 12 volt. Then what is changing is initially the circuit is set up in a darkened room and the voltmeter is connected across the LDR. So what is given here is the voltage of the LDR it is given. So voltage of the LDR, which is 4.71, whereas when it is in the lighted room, voltage of the LDR is 2.16 volt. These are the numbers given here. Now the question is, calculate the change in resistance of the LDR. Change in resistance. So the resistance calculation we have to do. Now let us have a close look on the circuit again. When it is in the darkened room, we don't know how much is the resistance of the LDR, but the voltage is given. So in the darkened room, the supply voltage, that is EMF 12 volt. We can calculate what is the current flowing through the circuit when it is in the darkened room. So I'm writing it as the current, or first we calculate the voltage across the fixed resistor, which is the EMF voltage over the resistance. Voltage drop, so this is the current, sorry, this is the current. So let us calculate the voltage drop across the LDR. Voltage drop across the LDR is there, so therefore we can calculate the voltage of the resistor, which is 12 minus 4.71, which is on calculation it is giving the voltage across the 7.3. So this is giving an answer of 7.3, approximately 7.3 volt. This is the voltage across the LDR, because we know the total voltage is voltage drop across the resistor plus voltage of the LDR. So to calculate, from this to calculate only the resistance voltage, it is subtracted. Similarly, let us calculate what is the voltage drop when it is in the lighted room. It is 12 minus, it is 2.16. It's approximately giving an answer of 9.84. 9.84. This is the voltage drop across the resistor in the lighted room. Now, so let us calculate what is the current flowing through the resistor. That is the voltage of the resistor over its resistance. So it is 7.3 and its resistance is 1200, which will give an answer of 0.006 amps. Similarly, here we can calculate what is the resistance, the current of the, not the, it is the voltage of the resistor over its resistance, that is 9.84 over the resistance is 1200, which is giving an answer of 0.08 amps. This is the current of through the resistor. Now, let us have a look on the circuit. The current through the resistor, is same as the current through the circuit current, which is same as the current through the resistor, which is same as the current through the LDR. So current through the resistor is 0.08, or this value means current through the LDR is also the same. From this, that means current of the LDR equals 0.006. From this we can calculate what is the resistance of the LDR, which is the voltage of the LDR over its resistance. What is the voltage of the LDR? 4.71. 4.71 over its resistance is resistance of the, sorry, not the resistance, voltage over current, IR, What is the current? How much is the current? Current is 0.006. So this is giving a resistance of 78.5. It is giving 78.5 ohms. Let's see what is the current of the resistor is this much, means current of the LDR is also 0. Because it's a series connection, 0.8 amps. Therefore, resistance of the LDR is voltage over the current of the LDR. What is the voltage? 2.16 over the current is 0.08. So the resistance value we are getting here as 27 ohms. So we calculated the current, we calculate the resistance of the LDR in the darkened room as well as in the lighted room. Therefore, the question is, what is the change in resistance of the LDR? This is the difference between these two numbers, 78.5 minus 27. This is giving an answer of 48.5. This is the change, 48.5. It looks little lengthy, but it's a 3 mark, so I did it separately. Darkened room, lighted room. In the darkened room, we calculated the resistance of the voltage of the resistor, then the current, that is same current as LDR. Then from that we are calculating the resistance of the LDR. Similarly, in the lighted room also, first we calculate the voltage of the resistor, then current of the resistor, which is same as current of the LDR. After knowing the current and the voltage of the LDR, we are calculating the resistance of the LDR. Okay, so it's giving a difference of 48.5 ohms. Now let's move on to the next question. The question is, a car battery is constructed using 6 cells connected in series with a combined electromotive force of 12. State what is meant by EMF. So electromotive force means it is the work done in moving unit charge around the whole circuit. So let's write what is the statement of EMF. It's the work done in moving unit charge across or around the whole circuit. Work done in moving unit charge around the whole circuit. Now let's see the circuit. There is an EMF of 12 volt. Then there is an ammeter, the voltmeter. Okay, let us write the values. The voltmeter reading, ammeter reading is 9 points. So this is the current. So the current I equals 9.83 amps. This is the current. And the voltmeter reading is 11.81 voltmeter reading. So the EMF is 12 and the voltmeter reading is 11 point, so this is V, terminal PD, 11.81 volt. EMF is 12, but the terminal PD is 11.81. Calculate the internal resistance of the car battery. So we know that the EMF E, it is terminal PD plus the voltage drop across the internal resistor. The terminal PD we know it is 11.8. So from this we can calculate what is the voltage drop across the internal resistor. EMF is 12 equals terminal PD is 11.81. So this is a terminal PD because it says that the voltage across the cell when a current is taken or the voltmeter reading, this is giving the terminal PD. So it is 11 plus VR. Therefore, the drop across the resistor is 12 minus 11.81. It's giving a number of 0.19, 0.19 volt. Now, from this, let us calculate. So, we got the answer. The voltage drop across the internal resistor is 0.19 volt. Now, what they want is the internal resistance R. Okay. So, R is equal to voltage drop over the current flowing. Now we know that the same current is flowing through the internal resistance means it comes somewhere here, no? We can show it somewhere here. The same current is flowing. So this is 0.19 over 89.83. So on calculation, we are getting the internal resistance as 0.019, approximately it is 0.02 ohms. This is the internal resistance. Now let's move on to the next part of the question. The student adjusted the variable resistor several times and recorded the corresponding values from the ammeter and the voltmeter. Describe how the values can be used to determine the internal resistance. Uh, of the battery using a graphical method. This answer we have already seen. So he has measured, he adjusted the variable resistor several times and recorded the values of ammeter and the voltmeter. So the voltmeter reading is the terminal PD. Then this is the current. Okay. Then on plotting, you will get it as a negatively sloped line. And for this one, the extending the graph backward and the y-intercept on the y-intercept of the line. So let us write it. EMF. EMF equals y-intercept. That means extending the line backward and get the y-intercept. Then R equals negative of gradient. Negative of gradient. So you can find out the gradient. This gradient and R is negative of the gradient. Describe how the values can be used to determine the internal resistance. Since I have drawn it here, I didn't write, but you can also write this. This should be the first sentence then. Draw a graph with the current along the x-axis and V along the y-axis. You can write that also, and you can describe these two methods, or you can just draw the graph with the proper axis marked. X-axis it is I, y-axis it is V, and you can write the method. EMF is y-intercept and R is the negative gradient. Now we are coming to the next part of the question. With the use, the internal resistance of a battery will increase. As time goes, the internal resistance of the battery will increase. Eventually, the power available from the battery will become too small to be used. A student calculated the power available from a battery of EM of 9 volt. So a battery of EM of 9 volt and internal resistance of R connected to a load resistor of capital R. He concluded that when the internal resistance had risen to zero point 0.5, this is a new R. So let us write it as R2, and this is the first resistor R1. Power dissipated in the 5 ohm resistor would reduce to 70% of its original value. Determine whether the student's conclusion is right or wrong. Okay. So let us say first one, R1 internal resistance is 0.1 ohm. The second one, second case R2, it is 0.5 ohms. Then the power dissipated, you are calculating the power dissipated in the 5 ohm resistor. Power dissipated in the 5 ohm resistor. So the power dissipated is, so what is the total resistance it is coming here? R total, we have R plus R1, which is 0.1 plus, what is the resistance? 5 ohm, 5. So 5.1 ohm is the total resistance we have. Therefore, we can calculate what is the current. Current is voltage over total resistance, EMF. Voltage means here it is EMF. Circuit current we are calculating. Okay. So EMF is 9. It is, let me write it as EMF itself, EMF. So it is 9 over 5.1. On calculation, it is giving 1.76 amps. Therefore, we can calculate what is the power dissipated in the first case, P1. I'm writing it as P1, which is I square R, which is 1.76. So this is first resistor, PR in the first case, PR for the first case, 1.76 square times the resistance 5, and it is giving an answer of, oh sorry, the current I square R 1.76 square when the internal resistance had risen to 0.5, the power dissipated in the 5 ohm resistor. So what is the value? This is on calculation. So 1.76, 1.76 times 5. It's giving an answer of 15.4. So this is giving an answer of 15.48. So 15.5 watts. So this is giving an answer of 15.4 watts. Let's see here. R total. The same steps we are doing it again. R plus R2, which is giving an answer of 5 plus, what is the second resistance? Second resistance is 0.5. 0.5. So this is giving an answer of 5.5. 5 ohms. Then we are calculating the corresponding current, circuit current, which is E over R total. which is 9. 9 over 5.5. It is giving a current of, let's calculate the current. 9 over 5.5. 9 over 5.5. This is giving a value of 1.6. It's giving a value of 1.63. 1.63 amps. Now we can calculate what is the power dissipation in the second case. It is I square R. We are using the same equation I square R, but the current is different. 1.63 the whole square times 5. This is giving a current of power of 13.5. It's giving a power of 13.5 watts. See, the first power was 15.5. The second case, the power is 13.5. But the student concluded that, or student said that, the power dissipated would reduce to 70%. Would reduce to 70%. So how much is the 70% of P1? 70% of P1 is, so on calculation you can see that 70% of PR1, it is less than 13.5. Therefore, so the student is incorrect. Now let us see the next question. A student is given the circuit diagram. Calculate a value for the voltmeter reading. You have to calculate the value for the voltmeter reading. Both the resistors are given, 12 and 5. The cell voltage is given, so we can calculate what is the current. Okay, so let us calculate the current. So 12 kilo ohms means it is 1200 ohms, and this is 55,000 ohms. So the current, the circuit current, I circuit equals voltage over R total, which is voltage is 1.5 over total resistance will be 1200, 12,000 plus 55,000. This is on calculation. It is 55,000, and it's on calculation giving an answer of 2.23. It's giving 2.23 times 10 to the power of negative 5 amps. On calculation it is giving, this is the answer. Then the question is calculate the voltmeter reading. See, this is I circuit, but you can see that the same current is flowing through the series connection. Therefore, the voltmeter reading is, so voltmeter reading across the 55 ohm resistor, kilo ohm resistor. Okay, so V equals I times R, which is 2.23 times 10 to the power of negative 5 times the resistance is 55,000. So on calculation, it's giving an answer of, let us calculate it. 2.23 times 55,000. It's giving an answer of 122,650 times 10 to the power of minus 5. So 1, 2, 3, 4, 5. It's giving an answer of 1.2 volt. This is the answer. So the drop across the 55 kilo ohm resistor is 1.2. 1, 2, 3, 4, 5, 1.2 volts. Now, let's see the next part of the question. The student sets up the circuit and observes that the reading on the voltmeter is lower than the value calculated in A. Explain two reasons for the lower voltmeter reading. Okay, so the voltmeter reading what we are getting here is 1.2 volt, but uh, the circuit he observed, but when he constructed the circuit, this is a theoretical value only, but when he did it and as an experimental value, the value he got across the 55 kilo ohm resistor is lower than this 1.2 volt. Explain two reasons for the lower voltage. So what the student said is V theoretical, or what we got V experimental. V experimental he got less than V theoretical. So this is he got theoretical only. This is a theoretical number. So he got less value. Explain two reasons for the lower value. Now see here, we have while calculating the voltage, we have not considered the internal resistance. See, in our calculations we have not taken the internal resistance. Okay, but experimentally when we are doing it, that internal resistance must get added up. So we can write the reason that the cell might have an internal resistance and a small drop in the internal resistance. That is one of the reason. In our calculation, theoretical calculation, we have not considered that. Okay, so let us put it as an answer. The first one, the cell might have an internal resistance and a small drop in the internal resistance. That is small drop in voltage, small drop in voltage, small drop in the internal resistance. See, small drop means small voltage drop. Okay, the cell might have an internal resistance and a small drop, voltage drop. Here the voltage drop in the internal resistance. They want two reasons. two reasons. Um, Another one is because when you are calculating the voltage, it is E minus IR. So if there is an R, there is a drop there. So you can write this also. Then another reason is the connecting wires might have some resistance and there may be some drop within the connecting wires also. So it is another reason we can write. So this is this equation. Then the second one is the connecting wires might have some resistance. The voltage drop in this resistance. This equation is for the first one. So these are the two reasons. Cell might have an internal resistance. Similarly, the connecting wires might have some resistance. Then the last question is, four identical resistors A, B, C, D are placed in a circuit. So you can see them as here. Then determine the power dissipated in each of the resistor. The power dissipation in each of the resistor. It's a 6-mark question. So resistance of each resistor is 2 ohms. So let us write the value here. This is 2 ohms. This is 2 ohms and this is also 2 ohms. All are 2 ohms. The power dissipated in each resistor. Definitely for power dissipation, we have to know the current, or we have to know the voltage also, current or voltage. So let us calculate the circuit current. This is the circuit current I. So same current is flowing here I, but here it branches. This branches into two other values. Okay. So how much is the circuit current? I circuit, the main current. I circuit equals the total voltage 10 over. Now look at the resistors, how they are connected. First resistor 2 ohm in series with a parallel combination of 2 ohms plus. So I'm writing all of them together. Let me write it. 2 parallel 2 plus 2. I hope you can follow this. That is, this is VA, this is VD, and this is B and C. Okay. So D parallel to the series combination of 2 and 2. Okay. Which is 10 over. So the series combination is 4. So it is 2 plus the series combination, it is 4, which is 10 over 2 plus C2 parallel 4. 2 parallel 4, we can write it as 2 into 4 over 2 plus 4. So this will give you 8 over 6. 8 over 6 will give a number of 1.33. This will give an answer of 1.33. So I'm using it here, 1.33. So finally, when I'm doing this, 2 plus 1, 3.33, 10 over, this is giving me a current of 3.03 amps. This is the current. So VA, our resistance A, is in series with the another loop. See, this is another loop. So that is 2 parallel 2 plus 2. So I'm getting a current of 3 point. So it is, let us take it as approximately 3 amperes. Now let us see the drop across each resistor. So let us see at least the drop across the first resistor. So the first through the first resistor, the same current is flowing. First resistor means A, the same current is flowing. Okay, so let me write how much is the drop across VA. So Ohm's law, I times R, which is 3 times 2, it is 6 volt. Therefore, the voltage across the loop, the full loop, voltage across the full loop. I told you I am calling this as the loop, this part as the loop. Okay, the voltage across the loop is total 10 volt. Out of that, 6 volt is dropped across the first resistor, it is 4 volt. The voltage of the loop is 4 volt, means the voltage of each branch is okay. Therefore, each branch, voltage of branch resistor D, it is 4 volt. Then voltage of B or voltage of C, it is half of this is 2 volt. See, we got it here. The loop voltage equals 4 volt. That means the first branch, here it is 4 volt, here 4 volt. Now here also 4 volt, that is for 2 people. So we are dividing 4 by 2, it is 2 volt. So we got the voltage drop across each resistor. Now we can calculate the power for each resistor. Okay, so I think I can do it here itself. Here itself I can do the power for this resistor. Power of A, it is V square over R, 6 square over 2. So it is giving 36 over 2, 18 watts. Then next one is this one. Power of D, it is V square over R. D is having a voltage of V, 4 square over, it is having a resistance of 2. So it is giving 8 watts. Then the next one is we have power of B. Power of B is V square over R. This is RA. This is RD. This is RB. So its voltage is 2 square over its resistance is 2. So it is 2 watts. The same power PC, which is V square over RC, 2 square over 2, it is giving 2 watts. So this is the power rating across or power rating of each one. This is 18, this is 8, 2. So we calculated the total current, then we calculated the voltage across first resistor, that is A, then voltage of the loop, from that voltage of the one branch, then voltage of the second branch, and corresponding power dissipations we calculated here. Now the next part of the question is explain without further calculation what would happen to the power dissipated by the resistance A if resistor D were disconnected from the circuit. See, that part to save time, I have already done it here. See, there was another resistor D, it is removed from there. Okay, now the circuit looks like this. Explain without further calculation. So when D is removed, what is happening? When D is removed, the overall resistance is decreasing. There was another resistance connected parallel, that is removed. So now A, B, C are connected in series. Okay. So we'll write when D is removed, the overall resistance increases. So circuit current decreases. So the circuit current decreases means uh, current through A decreases. Therefore, power of A, which is I square times resistor R. This will decrease. We are not calculating, but we know as I decreases, the resistance drop across resistor RA also will decrease. This is the question they are asking. Power dissipated by resistor A if R is removed. R is removed means total resistance increases, circuit current decreases, so power dissipated decreases. Then the next part of the question is, if the resistors in the circuit used in A were replaced with the filament lamps, the resistance of each lamp would be different depending on the potential difference across it. Explain in terms of particles why the resistance of a filament lamp increases with the potential difference across the filament. Okay, so here why the resistance is increasing with the potential difference. So we'll start with the as V increases, which is what they want. If the potential difference increases, so as V increases, what is happening? As V increases, the current in the circuit increases, I increases. So when the current increases, what is happening to the drift velocity of the drift velocity of current increases. So drift velocity increases because we know that I is proportional to the velocity, drift velocity, V drift. So when current increases, the drift velocity increases. So when the drift velocity increases, collisions among electrons increases, and when the collisions among electrons increases, they lose energy, and this energy lost will appear as heat energy, so heat will be developed. Okay, so when the drift velocity decreases, so what is happening? The electron collision increases. So collision of electrons increases, and they lose energy. Collision, no, they lose energy and heat is developed. So heat is developed means, so temperature increases. So temperature increases. So when the temperature increases, the lattice atoms vibrations will increase. So as T increases, the lattice atoms vibration will increase. So when the lattice atoms vibrations increases means it's difficult for the electrons to flow through, or the resistance will, okay, the lattice atoms vibrations will increase, So we can say rate of current flow increases. So R will decrease. This is what is happening. To explain in terms of particles, you have to write why the resistance of the filament lamp or why the resistance of the filament lamp will increase. Oh, this is increasing because the lattice atom's vibration rate of decreases and the resistance of the filament increases. I said in the opposite way. So a lattice atom's vibration will increase means it is difficult for the electrons to flow. So the current flow rate of current flow decreases, so R will increase. Sorry about this. So this is what. In terms of particles, why the resistance of the filament lamp increases. Resistance of the filament lamp increases because this is what is happening. So from the beginning, as the PD, voltage means PD across the filament lamp increases. So this is voltage or PD. PD increases, the current increases, so drift velocity increases, collisions increases. They lose energy and heat is developed. This lost energy is appearing as heat. That means temperature increases. When temperature increases, the lattice atom's vibrations will increase. So when the lattice atom vibration increases means it is difficult for the electrons to flow, pass through. So the rate of current flow decreases, that means resistance will increase.